Okay, I wanted to give you a little bit of an introduction to orbital motion. And to do that, I have this example. The other day in class, we talked about this Newton's cannonball, is what they call it. It was a thought experiment done by Sir Isaac Newton where imagine that you're at the very top of a very, very tall mountain. And very, very tall, like too tall for it to actually be in existence. But if you take this cannonball and you actually fire it with enough velocity, we talked about how it's going to start to orbit. And it's actually a projectile in that it's falling around the Earth because the only force that's acting on that cannonball is the force of gravity. And so this is an example of a projectile. And so what I wanted to do in this case was give you an example of how satellites, which are objects that revolve around some other bigger object, like a satellite, like some kind of man-made structure can be a satellite, or even the moon can be like a natural satellite because it revolves around the Earth. But in this case, our satellite is going to be Newton's cannonball. So I just kind of made up a problem. I said that this imaginary mountain that the cannonball is being launched from has an altitude of 100 kilometers above the Earth's surface. And then it also had a mass of 200 kilograms. We also know certain things about the Earth itself. We know that the radius of the Earth is 6.38 times 10 to the 6 meters. We kind of use that a lot in that pre-lab P.7.2. And if I were to represent on this drawing where the radius would be, it would go right there. And then I've got the mass of the Earth, which you determined in lab P.7.2, mass of the Earth, to be about 5.98 times 10 to the 24th kilograms. And so what I want to know is this. There's two questions. One, I want to know at what velocity would the cannonball have to move in order to be able to go in perfect orbit? And two, I want to know the period, or the time that it takes to go from here all the way around once. That's what's called the period, and we're calling that big T. Now, we have not yet talked about the period, so I thought we would talk for a second about how we could calculate the period. Well, the period is the amount of time that it takes to go around one time. And so we've talked about time in linear motion, where it talks about velocity in relation to this. Basically, we know that velocity is any time that there's a change in position over a change in time. Well, if I take this into consideration here, if I'm taking into consideration the whole motion here, if I call the time for one revolution to be the period, capital T, so time for one revolution is capital T, and the amount of space that covers, the distance that covers, is the circumference of a circle, which is 2 pi r. Circumference equals 2 pi r divided by my period should equal my velocity. And this is the fourth equation that is introduced in this unit. So we have talked about these four equations thus far. And in order to be able to answer these questions here, we're going to need three of these equations, and I'll kind of show you how. So the first thing that we need to do to solve this problem, after talking about that equation, is we need to consider what variables we know. First off, we know the mass of the cannonball, and we know the mass of the Earth. And so the next thing we need to ask ourselves is, do I know the radius of the orbit? Well, if I look at this picture, I know the radius of the Earth, but do you see how the radius of the Earth is not actually the complete radius? I have to take into consideration this radius plus the altitude of the cannonball above this Earth's surface, which is that. And so I look at this and I'm like, okay, I got that many meters, and then I'm going to have to add that many. Oh wait, that guy's in kilometers, so I better change this guy to meters. And so I change that to meters by moving the decimal 3 spots to the right. I've got 1,000 meters. If I add these two together, you're going to get an orbital radius of 6.48 times 10 to the 6 meters. And you guys can test that. So now the question is this. I want to try and figure out the velocity. Well, I look over here and I'm like, okay, what equations have velocity? Well, this one does, and this one does, but I don't know, oh, this is time here. I don't know the orbital period, so I can't use this equation. And this equation has mass of the object, of the satellite, the cannonball, divided by the radius, which I know, is equal to F net, but I don't know the F net. But the question is, what's causing the F net in this case? Well, that is the force of gravity. Boom, right here. I've got G, I always know G. I know the mass of the Earth, I know the mass of the cannonball, and I know the radius between them. So I'm going to use this equation here so that I can solve for my force of gravity. So I'm going to take force of gravity is equal to 6.67 times 10 to the negative 11. The big G, Newton's gravitational constant as discovered by Henry Cavendish, right there, times my mass of my Earth, which is 5.98 times 10 to the 24th kilograms, times my mass of my cannonball, 200 kilograms, divided by the radius, which is 6.48 times 10 to the 6, parentheses, meters squared. And so if I plug all this in your calculator, then I've already done the calculation so it won't take time. If you plug all that in the calculator, you're going to get the number of 1899 newtons. And so the force of gravity of attraction between the Earth and the cannonball at this orbital radius is 1899 newtons. Now, why? I didn't even ask for that question up here. Well, the reason that's important is because this is what's causing the imbalance of force. This is the centripetal force. Therefore, this is equal to F net. And so now I've got F net over here, which is equal to the mass of the rotating object, the cannonball, times the velocity squared over the radius. And so then I'm going to plug it into this equation. So I got 1899. 1899 is my F net. And that's equal to the mass of the cannonball, which is 200 kilograms, times my velocity squared, all over my radius, which is again 6.48 times 10 to the 6 meters. Now in this equation, I don't square it. Make sure you don't. And so then to isolate for v, I would have to multiply both sides by the radius, divide by 200, and then square root the velocity. When I do that, the velocity comes out to be 7,846 meters per second. And so that is the answer to my question up here. At what velocity would he need to launch that cannonball? Well, he would need to launch it at 7,886 meters per second. That is a very fast cannonball. What's even more interesting is the period. And so it says, how long is that going to take to go all the way around the Earth at that altitude? Well, I picked this equation here because it has velocity and radius, and I'm looking for delta for time. And so I could say velocity, which is 7,846 meters per second, is equal to 2 pi r, 2 times pi times my radius, which is again that 6.48 times 10 to the 6 meters, all over t. And so to isolate for t, I basically just flip places with those two and plug in and solve. What that t comes out to be is 5,189 seconds. And so you're thinking, well, this number means nothing to me because that's in seconds. Well, if you want to convert that to hours, all you have to do is divide that by 3,600 seconds. 3,600. And that's going to tell me how many seconds there are in 1 hour. So if I divide that, you're going to get that in hours. And so if you do that, the period in hours is 1.4 hours. So if you're thinking about this cannonball, if it was launched from an altitude of 100 kilometers above the Earth's surface, you have to launch that at first off a velocity of 7,846 meters per second in order for it to maintain circular motion. And it's also going to go around the Earth once every 1.4 hours. That's cooking. So anyways, this is an introduction to orbital motion. Now I understand that this is not the most ideal way to do it, but hopefully this works out all the kinks. Hopefully next time we'll work out all the kinks and we'll be well on our way to understanding orbital motion.